This is my title slide. You see on the right, Brian Josephson, or a caricature of him, John Bardeen on the left, and what Josephson is doing is trying to push a supercurrent through the tunnel. You'll see an image of the supercurrent in this cartoon, the paired electrons just above the cart coupled by a phonon connecting them. Now, I think before going any further, I should say a little bit about the background of Bardeen and Josephson. Probably most of this is already known. Bardeen, in 1957, created the first microscopic theory of superconductivity with Cooper and Schrieffer. And when you combine that with the fact that he had already won a Nobel Prize for creating the transistor with other colleagues, you can see that he was clearly one of the most eminent physicists of his day. On the other hand, Brian Josephson was a 22-year-old graduate student in Cambridge, and I find that to be quite a contrast. Brian Pippard, his research advisor, described it to me roughly as follows, that Brian Josephson had had a splendid career as an undergraduate studying mathematics and physics, and he decided that for his graduate project, he should do something practical, which to him meant do an experimental problem. So he was in an experimental group, not a theoretical group. You might say, fortunately or unfortunately, what came along, however, was that he was diverted from his experimental endeavors to do the theory of the Josephson effect. So in order to understand this yet more deeply, I want to talk about three different experiments that were done prior to the discovery of the Josephson effect, and I think you see the logical connection to what Brian Josephson did. The first of these comes from a book in 1948 by Fritz London about superconductivity. And London's view, I'll give you just the intuitive ideas. London's view was that, well, perhaps in a superconductor, the current is by charge carriers that all have the same momentum p. So that meant he could say in quantum mechanical terms that the wave function of these charge carriers must all have the same wavelength. Well, from that, you could make a hypothesis that, well, perhaps they could all be described by the same wave function, psi. Furthermore, the idea was that psi might have the same magnitude throughout the superconductor, and the only thing that varies is the phase. So here I show you a diagram of a closed superconducting loop, and it is, superficially at least, very similar to the Bohr theory of the hydrogen atom, the various orbits. So the point is the wave function has to be single valued at every point in space, and therefore, in order for it to close on itself, there has to be an integer number of nodes going around the loop. So the result of that thinking was that the current in the loop, which is proportional to the gradient of the phase, could take on only certain values because you could have only an integer number of wavelengths around the loop. And from that, you could say, well, the flux through the loop could be only in units of something which we know as the fluxoid or the flux quantum. So he predicted that and said the flux quantum would be h over e. The next experiment, or the first experiment really, was a test of that theory 13 years after Fritz London proposed the whole idea. Here you see Bill Fairbanks on the left, Baskin Beaver on the right, and this is their apparatus. the apparatus consisted of a cylinder of tin, this long thing that you see in the middle of the picture, coupling coils off the end, and I've tried to illustrate here flux lines coming out of the tin. Of course, that's only when the experiment is underway. So the experiment is to apply an external magnetic field with a superconductor above its transition temperature, lower the temperature below Tc for 10, turn off the external field, and measure what flux is in the cylinder. Fortunately here, I hope for your enjoyment, my daughter Heather helped me animate this experiment. And of course, it's kind of slow compared with what actually happened. But then on the right, you see the results of the measurements. On the x-axis is the applied field, and on the y-axis are the various quantized states that were seen in the experiment. The only difference from London's prediction is that the flux quantum is h over 2e rather than just h over e. The next experiment is by Hans Meissner. Hans Meissner is not the man who's famous for the Meissner effect. That's Walter Meissner. So this is somebody else. And he did a very simple experiment. He took two tin wires, coated one or both of them electroplated with electroplated copper, crossed them like this, pressed them together, and then measured the resistivity of the contact. And what he found was that if the copper was thin enough, a supercurrent could pass through it. And in fact, he got a numerical approximate result that the required thickness of the copper was about 300 nanometers. It couldn't be any thicker than that, or the effect wasn't present, which is pretty remarkable for this kind of experiment, I think. And in today's framework, the idea is that the copper thickness is something like the coherence length of the superconductor. So his conclusion was that if a normal metal is deposited on a superconductor, then the superconducting electrons, so to speak, can leak into the normal metal and make that superconducting. So that's what we call the proximity effect these days, and that was Meissner's discovery. The next experiment, the last experiment, is Ivar Guyver's experiment. He was a graduate student at Rensselaer Polytechnic Institute and working part-time at Bell Labs, I expect, not Bell Labs, GE Labs. I expect they were paying his fees. In any case, he took a course in superconductivity and learned about BCS theory and the fact that it has an energy gap. So fortunately, back at GE, he was in a group where there were one or two people who were interested in doing tunneling experiments, but of course into insulators or metals, things of that sort. And so he said, well, what would happen if we tunnel into a superconductor? And it was explained to him that tunneling into a superconductor to see an energy gap is a totally different thing from tunneling into an insulator. Insulators have energy gaps that arise from the crystalline structure of the material. And that's not the case of the BCS energy gap. That energy gap is a property of the many-body electron system that constitutes the superconductor and has nothing, that's only a slight exaggeration, to do with the lattice structure of the metal. So the obvious thing to do was do an experiment and find out what would happen, and there was no theory for him to use to define his experiment or anything. So he did the experiment. You can see up in the corner there, it says an aluminum, aluminum oxide, lead tunnel junction. And the first data is with the lead above its transition temperature, and it's purely a resistor. Then he lowered the temperature and eventually got down to 1.6 degrees Kelvin and found that, voila, the curve is quite different. Major success. The next step was that, as many people would naturally do, I suppose, is say, oh, I don't want to really look at just the IV curve. I want to look at dIdV versus the voltage. And lo and behold, there's a peak. And so Guyver's jump of imagination was this is reflecting the quasi-particle states of BCS theory in the superconductor. And furthermore, well, another set of words that needs to be said here is that this represents the density of states in the many-body problem. And this was a complete revelation to the community of physicists. So John Bardeen was an advisor to GE Labs who came and criticized the work that was going on there, probably saying good and bad things. And he went to the GE Labs very shortly after Guyver's experiment, purely by accident. He went back to the University of Illinois and said, oh, this is new physics. I have to understand what's going on here. And so he wrote a paper, the one I list up here, about tunneling in a many-particle system. Now, his idea of a theoretical analysis, as Bardeen is famously known, was largely intuitive. He said, well, this has to be the wave function in the normal state, this has to be the wave function in the superconducting state, and then there's some kind of thing connecting the two states, some kind of tunneling wave function, and found that he could demonstrate that the tunneling current could agree with Guyver's experiment. So he wrote this paper, and what I'm quoting here is just an incidental comment that was in the paper, not related to Guyver's experiment at all. He says, one sees that delta, the energy gap, will drop to zero very rapidly in the barrier. In effect, electrons in this region are not paired, and the wave function is essentially the same as in the normal state. Well, as you can guess, that's going to bring him into conflict with Josephson. So let me summarize these three things. I find it kind of interesting to do that. So Guyver's experiment brought theorists' attention to the idea of tunneling. They had not worked on that previously. Secondly, flux quantization showed that the superconducting state could be described mathematically very simply, namely by a single wave function and a phase. So that's the flux quantization experiments established that that was a legitimate picture. Finally, the proximity effect demonstrated, as I say here, that supercurrents could exist in non-superconductors. So you've got to extrapolate that maybe to insulators. What I'm going to talk about next is a more mathematical theory of tunneling that came up to replace the work that Bardeen had done. Now, Bardeen probably thought his work was the definitive work, but some other people disagreed. And so I'm going to go into the details very, very briefly of some of the subsequent work. Before doing that, I'm going to change the direction of what I'm talking about. And some of you will think this is probably kind of weird. Sorry for that. This will last about 30 seconds, and I'll get back to the tunneling thing. The important thing I want to bring to mind is, what is mathematics? Now, everyone in this audience, I think, or very nearly, has studied mathematics pretty extensively. And therefore, if I walked up to you and said, what is mathematics? You'd probably have some kind of reasonable statement. But I find people's opinions certainly differ. Well, anyway, if you go on the web, which is the source of all knowledge, you find that the main theme that is echoed there is that mathematics is the attempt to find all possible patterns relating abstract symbols. I think if you think about that just a moment, you'll say, yes, that's the case. That is what mathematics is. And what I want to do for the moment, very brief moment, 30 seconds, is talk about patterns, because patterns are far more widely in our culture than just in mathematics. And I think there is some patterns that are exceedingly beautiful. So I want to show you a visual and audio presentation of some beautiful patterns. Well, I hope you enjoyed that as much as I do. There's something about seeing the visual pattern of the music simultaneously with the sound that just charms me. Okay, let's move on. The group of Cohen, Falikoff, and Phillips at the University of Chicago decided, well, Bardeen's theory of tunneling is not all that great. We can do better than that. So they said, let's write down the Hamiltonian for the tunnel junction. And in their paper, they say this is an exact Hamiltonian. I'll say, well, maybe. Anyway, you see here is the Hamiltonian of the normal state, plus a Hamiltonian of the superconducting state, plus a Hamiltonian for the tunneling region or the transfer Hamiltonian. Now, I'm not going to go into any great details here, but the form of the tunneling Hamiltonian is given here. And this is a wonderful example of a particular pattern in mathematics. Oh, by the way, I need to apologize. I wasn't able to coax the software to put daggers to distinguish a creation and destruction operator. Anyway, the T's are the matrix elements for tunneling, and the A's are the electron creation and destruction operators. And so basically, Cohen, Falikoff, and Phillips said, this is what the tunneling Hamiltonian has to look like. As far as I know, that's just pulling it out of the air, but so what? So Josephson in Cambridge received a preprint of that paper, and he in effect said, this is just what I've been looking for. I mean, Josephson's great skill, genius you call it, was at doing mathematical analysis. And he says, from this Hamiltonian, I can calculate everything I want to know about the tunneling barrier. So here are his results. And I won't go into them. You see the top equation is just the DC current, and the bottom equation is the AC current. Well, one thing I left out, didn't put in a slide as a reminder, is that when Cohen, Falikoff, and Phillips submitted their paper to physical review letters, John Bardeen received a copy, and being the person he was, that I understand superconductivity, he wrote, or according to Jim Phillips, one of the co-authors of CFP, said that he called the editor, Samuel Goudsmit, and said, this paper should not be published, it's wrong. So the editor said, acting as a politician, that, well, what you should do is communicate directly with the authors and see if you can't resolve this problem. So they did that, and I can quote Bardeen as making a statement. They exchanged letters back and forth, making a statement to Cohen, Falikoff, and Phillips that, well, you assume that the problem is this is the correct Hamiltonian, and its solution, which I consider to be trivial, is the problem to be solved. And so that's what their paper is about, is how you work through the mathematics of this Hamiltonian. He says, whereas I view the problem as what is the correct Hamiltonian. So the result of this exchange of letters was that they wrote a footnote which said, maybe there are physical effects which have not been taken into account in this analysis. Nevertheless, the analysis of Cohen, Falikoff, and Phillips correctly explained Guyver's results. Okay, sorry, now back to Josephson. So Josephson publishes his paper, and as Bardeen was prone to do, he's always on top of every subject that was prominent in the topical area of superconductivity. He writes yet another paper and says, Josephson is wrong, folks. You know, this can't happen. I've mentioned before that pairs cannot go through an insulating barrier. That brings us up to LT8. LT8 was in London in 1962, and Paul Martin was the chairman for a session to discuss tunneling. And Martin was aware of the difference of opinion of Bardeen and Josephson and said, oh, it would be nice if we could have them both come to this session and jointly discuss their differences. So he did that. Now, what's unfortunate here at the moment is you might think, well, I'll show you a video of the debate. Well, I can't do that. In fact, there's no audio recording of the debate. And furthermore, in these proceedings, there's not even a mention that Josephson attended the conference. He came down to the conference, debated with Bardeen, got on the train, and went back home. That was that. So I have to fill in by talking with people who were there. And the picture that emerges is that Josephson got up, gave his talk first, explained how he thought the Gorkov formulation of BCS, which involved a phase, led to his results. Then Bardeen got up from the back of the room, I guess, walked forward and repeated his comments from his explanation of the Guyver experiment, concluding with the notion that pairs could not exist in the tunneling barrier. And that's where the whole story was left at the end of the conference. Well, Vinay Ambedkar was a young theorist at the time, just newly appointed to the faculty at Cornell, and he wrote a paper with his first graduate student. Oops, that's not right. How did that happen? Oh yes, that is right. Excuse me. And I talked with him about this on the phone. I said, how succinctly can you describe the difference of opinion? And this equation here is from Ambedkar. Ambedkar, by the way, said to his student, his new student, he said, I've heard there's a dispute between Bardeen and Josephson. He said, Bardeen is my hero. Bardeen is always right. So he said, let's find out why. So they started working through the theory and ended up, as Josephson had, with the Gorkov formulation of quantum mechanics. And this is the, you might say, killer equation for Bardeen. What you see on the right is the wave function, delta. The the coordinate system here is the coordinate x going through the tunneling barrier. So what this says is that, well, the quantity on the left is the pair amplitude in the theory. So what this says is that the integral of the product of some kernel and the delta function, excuse me, not the delta function, and the energy gap function is this amplitude for the pair tunneling. And it turns out that the K function, the kernel of the integral, has a range of the order of the coherence length of the superconductor. What that means is quite simple. Delta can indeed be 0 at some point, or even a range of points within the superconductor. But if K is big enough in X, then it can pick up areas, regions where pairs exist in the superconductor, and therefore F, the pair tunneling amplitude, is indeed finite. Bardeen said delta being 0 meant F had to be 0. Wrong. F can be finite with delta 0. I think that's the substance of the discussion. Well, what are the consequences of this? I'm glad to see that John Clark is here, one of my heroes. He did an experiment way back in 1968 which said, let's find out whether Josephson junctions made of different materials produce the same voltage in the AC Josephson effect. So he did this, he created this experiment. And the way I want you to think about it is, besides the two Josephson junctions, there's a superconducting loop here so that he can bias the junctions on a particular voltage step. And he makes each junction on the same step, even though the junctions are different materials. Closes the superconducting switch, and then with his superconducting galvanometer, looks for a circulating current going around the loop. The point is that if the voltages are different, the only impedance in this loop is the inductance. And therefore, if there's a difference in voltage, then a circulating current should build up in the loop. He couldn't detect one. So his conclusion was that the Josephson voltage resulting from different material junctions was the same to a part 10 to the 8th. Very impressive result. Well, 19 years later, you see this bottom header, 1987, Jim Lucan's group in Stony Brook said, hey, we can do this experiment much better these days. Things had come quite a ways in the intervening years. So they did basically the same experiment, and their result was, I hope I have this right, 11 orders of magnitude approximately better than John Clark's. So I was almost magically affected by the idea of doing an experiment which established something to this incredible precision. So this is truly a personal matter at this point, but I want to talk about that. This is football season, of all things, yes? Got to quit. Not quite. This is the Bronco Stadium in Denver. Everybody knows these stadiums are very big things, okay? So I want to use that as the scale for things. And let us ask the question, let's fill Bronco Stadium all the way to the rim with sand. And then what we do is find some research assistant, some young research assistant, and tell him to go out and count the grains of sand. So in the next picture, we're looking for somebody who's working on this project, and lo and behold, we find somebody. And the result of all this is that when the sand reached, as he counted the grains taken one by one from his bucket, when the number of grains of sand was 10 to the 18th, the stadium was far from being filled. But when he got to approximately 10 to the 19th, he said, oh, the stadium's full. So 1 part in 10 to the 19th means 1 grain of sand compared with all the grains it would take to fill the Bronco Stadium. That's Brian Josephson's legacy in my mind. Thank you.
There a question or two for Don?
Oh yeah, leakage currents. Yeah, I suspect, well, you know, one of the things you notice when you look at the history, that Bardeen thought Meissner's experiments, if he even knew about them, were just too primitive. You know, you're taking 2 wires, crossing them, pressing them together. Who knows what you're doing at the interface? That's you know, a legitimate question. Anyway, that's one of the few things that happened that Bardeen didn't care to quote about. And in fact, it happened that Cooper, one of his colleagues in BCS, became interested in the proximity effect, wrote a paper about it, talked about it, and tried to convince Bardeen that it was real, it was true, and Bardeen wouldn't have it. So that's about all I can say on that subject.
Thank you very much, Don. Let's thank our speaker again.